My name is Fernando Jimenez. I'm from the MEX VPN team, and I'm here to talk about IPsec anti-replay check failures and invalid SPI errors. Um, this is a very interesting feature that IPsec IOSXE routers has. So we're going to discuss about them, how to detect them, and how to conclude if indeed the replay drop is expected or not. So this is the agenda for today. Um, First, we're going to discuss about anti-replay check failures. Then we're going to talk about the IPsec replay drops, how to troubleshoot those IPsec replay drops, the solution for IPsec replay drops, and after we discuss this, let's say point 1 through 4, it's going to be one section. Then we're going to discuss about the SPI errors and invalid SPI recovery. Finally, we will have a session of questions and answers. Okay, so just for your information, so basically today we're going to discuss about all of the packets that are going through the VPN tunnel. So I put this image as an example. So we're going to focus only on the cars. The cars are the packets that are going through the tunnel, through the VPN tunnel, right? But since we are technical guys, so I put another image. So here, H1 is forming a VPN tunnel with H2 device. And as you can see, well, the VPN tunnel is the green tunnel that we're seeing here. And as you can see, we're going to focus on the packets that are traversed through the VPN tunnel. These little yellow rectangle boxes are that we're going to focus on those packets. Okay, so let's begin. Anti-replay check failures. So as an overview of the replay attacks. So a replay attack is a form of network attack in which failed data transmission is maliciously or fraudulently recorded and later repeated. It is an attempt to subvert security by someone who records legitimate communications and repeats them in order to impersonate a valid user and disrupt or cause a negative impact on the legitimate connections. Meaning that the replay attacks could be a man in the middle that replicates a VPN packet claiming to be a packet from a user that belongs to the VPN tunnel. So we are going to protect from those attacks, and we are going to protect with the replay check protection. So what is that? So the IPsec replay check protection is a sequence number that monotonically increases is assigned to each encrypted packet by IPsec to provide anti-replay protection against an attacker. The receiving IPsec endpoint keeps track of which packet it has already processed when it uses these numbers and a sliding window of acceptable sequence numbers. So in other words, so as you can see here, we are seeing ESP traffic received, meaning the packets that are traversing through the VPN tunnel. As you can see, each packet has an ESP sequence number. So below you will see a window, which is called the IPsec replay sliding window. And by the default on iOS, IOSXE routers, this value will vary depending on the box. But basically, the default value is going to be a sliding window of 64, meaning that in this case, as an example, we're going to receive packets from ESP sequence from 101 towards 164. So if we receive the next packet, which has a sequence number of 165, then the sliding window will move. All right, so where this window is going to move, and therefore we are not longer waiting packet 101. And here is a clear example. So we received the ESP traffic with an ESP sequence number of 166, and it's going to be valid. But since the packet 99, it's received, it is going to be dropped because we are not longer expecting that packet because it is already received or the sliding window has moved. And as well, here is another example, packet 161. Well, this packet, we already received a packet 161, but we already received one. It's going to be a duplicate packet. And therefore, so in the next slide, well, here are going to be how the IPsec replay check protection works. So when an IPsec tunnel endpoint has anti-replay protection enabled, the incoming IPsec traffic is processed as follows. So first, if the sequence number falls within the window and has not previously been received, the packet has its integrity checked. If the packet passes the integrity verification check, it is accepted, and the router marks this sequence number as received. Number two, if the sequence number falls within the window but has been previously received, the packet is dropped. So this is like the example that I mentioned previously. Oh, my bad. We received a packet with sequence number 161, and we already received another packet with the sequence number of 161. Well, that packet, since it is duplicate, it's going to be dropped. Number three, if the sequence number is greater than the highest sequence number in the window, the packet has its integrity checked. If the packet passes the integrity verification check, the sliding window is then moved to the right. For example, if a valid packet with a sequence number of 189 is received, then the near right edge of the window is set to 189, and the left edge is 125. That is taken with the form, well, so for example, with we receive a sequence number, a packet with a sequence number of 189, then the window is going to move. The right edge is going to move to that value, 189, and we are going to rest 64 because the sliding window has a value of 64. And the left edge will start of 125. And number four, if the sequence number is lower than the left edge, the packet is dropped and recurring within the replay counter. This is considered an out of order packet. Again, so we have, in this example, we have the left edge that starts at 101. And if we receive a packet below this sequence number, it is going to be dropped and considered out of order packet. So what happens if the router detects this kind of errors? So in the cases where a replay check failure occurs and the packet is dropped, the router generates a syslog message as it follows. So the router is going to print this message: IPsec replay error, IPsec security association receives anti-replay error, DP handle, a number of the DP handle, the source address, which is coming in the packet, so it's going to print the IP address of the peer, destination address of, which in this case, it's going to be the affected router that prints this error, and an SPI value. So I just want to emphasize this, that the anti-replay protection is an important security service that the IPsec protocol offers. So if you want to disable this, it will have security implications, and this must be done with discretion. So after this, well, you are going to be able to troubleshoot and determine if indeed we need to disable the anti-replay protection or not. Okay, so what happens if we have drops? So there are going to be some errors or problems that will cause by these IPsec replay drops. And well, the main purpose of the replay check is to protect against malicious repetitions of packets. However, there are some scenarios where a failed replay check might not be due to a malicious reason. So reason number one, the error might result from a sufficient packet that is reordered in the network path between the tunnel endpoints. This can likely occur if there are multiple network paths between the peers, like asymmetrical routing, etc. So this kind of errors might be expected because of that. Number two, the error might be caused by unequal packet processing paths inside the Cisco IOS, IOSXE, IOSXE SD1. For example, fragmented IPsec packets that require IP reassembly before decryption might be delayed enough that they will fall outside of the replay window by the time they are processed. So if, of course, the packets are being fragmented, this might cause this kind of errors, and the IPsec replay drops might be expected. Number three, we need to consider if the QoS is enabled on the sending IPsec endpoint or within the network path. Of course, this is another thing that might delay some of the packets that are being sent through the VPN tunnel. Number four, it's that a network configuration operational issue can duplicate packets as they transit the network. This is another issue that might, or another reason that might cause these replay drops. And number five, and this is why we have the IPsec replay drops. An attacker, man in the middle, could potentially delay, drop, and duplicate the ESP traffic. Okay, but now how to troubleshoot these IPsec replay drops? Okay, so as it was mentioned previously, it is important to understand why these IPsec replay drops. So we need to be aware of our network or customer's network before doing an action plan. So the key to troubleshoot IPsec replay drops is to identify which packets are dropped due to replay. So we can use packet captures to determine if these packets are indeed replayed packets or packets that have arrived on the receiving router outside of the replay window. In order to correctly match the drop packets to what is capturing the sniffer trace, the first step is to identify the peer and the IPsec flow to which the drop packets belong and the ESP sequence number of the packet. So the Cisco IOSXE has a really useful tool, a feature that is called Data Path Packet Tracing feature. And first, this feature can be used in the situation when the replay drop is observed. First, we need to identify the syslog message that is thrown by the IOSXE router. So we will see, again, as it was mentioned previously, an error similar to this. First, it will appear as it follows: IOSXE platform, QFP thread, etc., a random value. And below, after this message, it will appear IPsec replay error, IPsec SA receives anti-replay error, the DP handle with the value on number 3, the source address, which in this case is going to be 10.2.0.200, destination address 10.1.0.100, and the SPI value. So now, in order to help identify the ESP sequence number for the packet drop, complete these steps with the packet tracing feature. So first, we need to set up a platform conditional debug filter in order to match the traffic from the peer device. So we're going to configure this debug platform condition IPv4 with the IP address 10.2.0.200. If you remember correctly, this is the IP address of the source address that is being displayed on the syslog error. And then we are going to start this debug platform condition with the debug platform condition start. So now, then we enable packet tracing with the copy option in order to copy the packet header information. So we will do this with the following commands: debug platform packet enable, debug platform packet trace packet, and a number. So this is going to be 64, but we can capture more packets if we want. For example, we can put 90, 100, 200, etc. And then this is an important, a key aspect to take into consideration. Debug platform packet trace copy packet input layer 3 size 100. Okay, so We have enabled this packet tracing feature, and when the replay errors are detected, we can use the packet trace buffer in order to identify the packet drop due to replay. And the ESP sequence number can be found in the packet copy. So for example, in this scenario, in this example, a lot of packets are coming into the router. We just put our filter, our debug, our conditional debug, etc., and we receive these packets. As you can see, packets 0 through 5 are consumed, meaning that these packets are being processed correctly. However, packets 6 and 7 are being dropped, and the reason it's going to appear as follows: 053 IPsec input. So probably one of these packets are being dropped to this IP replay check failure. Okay, so since we already detected these two packets, well, we can investigate more about that packet. So we are going to check packet number 6. We can verify more aspects of that packet with the following command: show platform packet trace packet, and we specify the number 6. So here it's going to appear a summary. In the summary, it will appear that the input it's coming from gigabit 400 and the output tunnel 1. The state, it's been dropped as it was mentioned in the summary. And in the path trace, we're going to get more information. So we have the source IP address, the destination IP address, and the protocol. As you are aware, whenever we are sending traffic using ESP, the protocol is going to be IP protocol 50 or ESP. Now, the action, it's going to be decrypted. However, we detected that it's going to be dropped. And we are going to match the SPI value that appeared on the syslog error message. So this matches, and the action is dropped. And why is it dropped? Because of the anti-replay check failure. Now, here, the ESP sequence number has an offset of 24 bytes that starts from the IP header, or 4 bytes of the IP packet's payload data. As it is emphasized in bold here, as you can see, the ESP sequence number for the drop packet is 6. So it has that this is going to be the sequence number. So we can focus on this. So we can count the numbers of the octets: 1, 2, 3, 4, 5, 6, and number 7 is going to be where we will need to focus to identify the ESP sequence number. So this is using the IOSXE database packet tracing feature. But now we can collect packet captures using embedded packet captures on the router. And this will double check and confirm if the packet is out of sequence. So once we collected the packet capture, the encrypted data, we can proceed with further analysis. So in here, in order to enable or check the sequence number of the ESP frames, we can go to Preferences on Wireshark, select Protocols, we select ESP, and check the sequence number of ESP frames. So this is important. And now, now that we have selected that, we can go to the Analyze Expert as it follows, so we can start checking the ESP sequence numbers. So here is going to be a warning, and it says ground sequence number for SPI, and this is going to be the SPI that is appearing, 1 missing. And we're going to count the number of packets that are being that have ground sequence number. So in here on the packet capture, we have a snippet, and we select one packet that has this ESP sequence. As you can see here, we determine here the sequence, and if we expand the option of encapsulated security payload, it's going to appear here the ESP sequence number and the expected sequence number. So here on the expert info will show a ground sequence number. So here's a way to detect better what is the ESP sequence number that we expect and the shown ESP sequence number. And then we can detect, okay, uh, these packets should be valid or not, etc. So we have three main solutions after we perform the troubleshooting. So the first one, it is a valid packet that has been delayed. So packet captures will help to confirm if the packet is actually valid and if the problem is insignificant due to the network latency or transmission path issues, or require a more in-depth troubleshoot. For example, the packet capture shows a packet with a sequence number of X, a random value, that arrives out of order, and the replay window size is currently set to 64. If a valid packet with sequence number X plus 64 arrives before packet X, the window is shifted to the right, and the packet X is dropped to a replay failure. So in such scenarios, it is possible to increase the replay window or disable it, depending on what you have found during the troubleshooting process. And I'm going to show in the next slide how to modify the window size or disable it. Number two, it is due to QoS configuration on the sending endpoint. So we'll need to identify if indeed the sender has QoS enabled and how QoS is affecting the ESP traffic. So this is it will be worth it to check the QoS configuration if there's a shaper in place, a polisher, etc. And number three, it is a duplicate packet that was previously received. If this is the case, then two or more packets with the same ESP sequence number with the same IPsec flow can be observed in the packet capture. So in this case, the packet is dropped as expected and IPsec replay protection is working as intended. So in this scenario, of course, we might have a possible attack and will be worth to check it internally with security in order to see who is that guy that is intended, well, trying to break our communication or to pretend to be someone else. Okay, so if we fall in point number one, well, we are going to configure or disable the anti-replay window. So this is for iOS XE, iOS routers. So we go to configure terminal if we want to modify the window size, configure terminal, and we enable the command crypto IPsec security association replay window and the value of the window size. So as a default, as it was mentioned previously, it is 64, but it will depend on the hardware as well and the version. So it could be 64, then 128, etc. You can specify a value. I believe the maximum value will be 4096. And if you want to disable the anti-replay window, we can just type the command crypto IPsec security association replay disable. Okay, and this is for iOS XD1. So this is a note, an important note. In iOS XD1 images, it's not possible to disable the replay window for SD1 IPsec tunnels. But we can modify this value with the following command. So as it states here, by default, the sliding window is set to 512 packets, so it's considerably huge in comparison with other iOS XE routers. And it can be set to any value between 64 and 4096, that is power of 2. So you can specify a value of 64, 128, 256, 512, 1024, and so on until 4096. This is how you modify the replay window number. So you can type security, IPsec, replay window, and the number of the window size that you want to configure. Okay, so this is all from the anti-replay window. Of course, in the presentation, you will have more documentation about it, but I'm going to make a pause. If you have any question regarding that, well, you can ask it right now if you want.
So Fernando, thank you first of all for presenting about this topic. I have a couple of questions here. So you were talking about the range of packets, and for your example, starting from 101 to 164. Uh, and you mentioned that we're gonna wait for the right and left edge, or that I'm assuming. Um, if I get let's say packet number 160, and at the end I get packet 101, does that still count as anti-replay drop, or as long as I get all the packets within that window, I'm gonna be good and I can reorder them, no issues?
No. So you mean that if you receive a packet, for example, 165 and
No,
then
no,
101, is that your question?
no. So if I get 160,
Mhm.
and I get 101 later.
Yeah,
Is-
it will be accepted. For example, if you do not receive a packet that has a greater sequence number, for example, in this scenario, in this slide, we have this IP replay sliding window. If we do not receive a packet with an ESP sequence number higher than the rate H, we are going to accept all of the packets that belong into the sliding window, meaning that it doesn't matter if they came out of order. So meaning you receive 163, but you can receive 101. The problem might come if you receive a packet higher than the right edge, meaning 190, for example. The right edge window will move, and there we're not longer going to accept 101.
Okay. And you mentioned that if we get a duplicate sequence number, we're going to drop it. But does that cause the counter for the anti-replay to increment, or is that just silently dropped and the device moves on?
No, it's going to the counter of the replay check protection or the drop will increase, and it's not going to be a silent drop. You will see an error like this.
Okay.
Mm-hmm.
And my final question here is, if I receive a packet in the middle, like I mentioned earlier, the 160, does it know by default what is the right and left edge? Is there a way for the packet to know in advance about what is the right and left edge before it arrives?
Well, the packet will not have that information. Actually, the router is that has that information. So the packet will not contain that information. The packet only contains the ESP sequence number, and that's all. The router is the one that is going to do all the math, all the moving of the sliding window, etc.
Understood. Thank you.
Sure. Any other question? Okay. Good. So we can proceed. Now that we have discussed this, we are going to move to one common issue that is going to be SPI errors and invalid SPI recovery, how they work and how to troubleshoot it. So one of the most common issues in IPsec is that security association or SAs can become out of sync between the peer devices. As a result, an encrypting device encrypts traffic with SAs that it peers does not know about. These packets are dropped by the peer and this message appears in the syslog. So if the security association's SAs become out of sync, we're going to print this error. Crypto -4 received underscore packet underscore invalid underscore SPI. And the decaps. Received IPsec packet has invalid SPI for destination address. So this is the destination address, the packet that is coming into the router, the protocol that we are using, IP protocol 50 or ESP. We're going to have a value of the SPI and the source address. As you can see, in this scenario is 10.1.1.1. And in order to see in the router, uh, if the packet, well, if the counters are incrementing for invalid SPI errors, well, we can issue the command show platform hardware QFP active statistics drop pipe include IPsec. So we can filter everything for IPsec, and then we are going to see here all the drops. So Uh, we are going to focus mainly, as you can see in the arrow, with IPsec input. Now, another command to double check this information is with the show platform hardware QFP active feature, IPsec data path drops all, pipe include SPI. And what we're going to focus, it's going to be the counters for this value. In underscore us underscore version 4 packet SA not found SPI. The key word here is not found SPI. Okay, so this is how we can check the counters and if we receive those errors, so we can see how many packets are being dropped due to these invalid SPI errors. Now, in order to resolve this issue, Cisco recommends that you enable the invalid SPI recovery feature. We can enter the command crypto ISACAM invalid SPI recovery. And here are some important notes that we can that describe the use of this command. So first, invalid SPI recovery only serves as a recovery mechanism when the security associations are out of sync. It helps to recover from this condition, but it does not address the root issue that caused the security association to become out of sync. So in order to better to understand the root cause, well, we can enable some debugs, ISACAM and IPsec debugs or IKV2 debugs, depending on what you have on your tunnel. And if the problem occurs often, then obtain the debugs and attempt to address the root cause. So basically, troubleshoot and determine and analyze the debugs. But this is just like, let's say, a band-aid to recover from the invalid SPIs. Now, there is a common misconception about the purpose and functionality of this command. Even with this command, Cisco IOSXE already performs a type of invalid SPI recovery functionality when it sends a delete notification to the sending peer for the security association that is received. So meaning that, imagine that we receive an invalid SPI packet on the router and we do not have enabled this command, the crypto ISACAM invalid SPI recovery, automatically the receiving router will send a delete to uh, the sender, the router sender, and this will bring down the VPN tunnel. And if traffic is passing through the tunnel or wants to pass traffic through the tunnel, then everything will be renegotiated and bring a different a new VPN tunnel with different SPIs and security associations. And well, the crypto ISACAM invalid SPI recovery command attempts to address the condition where a router receives IPsec traffic with invalid SPI, and it does not have an IKE SA with that peer. In this case, it tries to establish a new IKE session with the peer and sends a delete notification over the newly created IKE SA. However, this command does not function for all crypto configurations. The only configuration that this command works for are static crypto maps where the peer is explicitly defined and static peers that are derived from instant sharing crypto maps, such as VTIs. So here is a box of the crypto configuration, and here it's if the invalid SPI recovery works or not. So for example, static crypto maps do work, dynamic crypto maps don't, and so on. So basically for SD1, SVTI and DVTIs are the only IPsec tunnels used for IOSXE SD1, and the only invalid SPI recovery will be for SVTI. Okay. Now, how to troubleshoot these intermittent invalid SPI errors. So there are many times where the invalid SPI error message occurs intermittently. So we do not know when this error will appear. So it is hard to troubleshoot these kind of scenarios, but of course we have a really useful tool that most of all, well, we have used in such scenarios, which is called Embedded Event Manager, or better known as EEM scripts. And here I'm attaching a link where it describes how to create an EEM script. Of course, this EEM script, well, you can configure it depending on what you want to capture. So this is an example of an EEM script. So packets are dropped on the peer with this message log on the syslog. So this is the syslog that the router is printing. Take note for the destination address, the SPI, and the source address. Okay, so it is important to know what happens before the syslog message. So we need to uh, to configure debug commands, and as well, it is important to mention that we need to enable cryptic condition commands just to focus on one peer. Imagine like we have a router with 2,000 tunnels. Of course, if we enable a debug without a cryptic condition, we are going to capture information for all of the tunnels, and probably the router might crash. Um, so it is important to enable a conditional peer, conditional debug. And in this scenario, we're using IPv1. So we are going to enable these debugs, debug crypto ISACAM, debug crypto IPsec, or debug crypto engine. If we are using an IPv2 tunnel, then of course we can enable debug crypto IPv2 or debug crypto IPv2 errors, etc., depending on the VPN tunnel that you are using. So we enable this debug so we can continuously analyze what is going on. And here on the EM script example, we are going to focus when the syslog error appears. So this is going to trigger the EM script when the syslog patterns appears, and this is going to be the syslog pattern, sorry. Crypto received packet invalid SPI source address. And here are all the commands that we want to retrieve whenever we want to this issue happens or this syslog error is print. Remember that all of the debugs are continually running, and besides that, we are going to capture all this data. You can here in this example we put a DMVPN because for this particular scenario, this is a DMVPN tunnel. However, you can modify these commands as well. And remember to append all of the debug outputs. It's not here, but append all of the debug outputs uh, to a disk or to the flash, etc. And basically, that's all. Here are all of the references for, well, that we used for this presentation. If you want to have more information about the IPsec anti-replay check failures, you can visit this document, how to configure, expand, and disable the anti-replay window, and as well some security configuration guide for iOS XE SD1, which is really useful for you. And as well, if you want to get more information about invalid SPI recovery, and as well, I'm putting here the EM scripts if you want to use it troubleshoot. So hopefully this presentation was useful to you. Of course, we need to practice it. And well, we're going to send this presentation so you can have it as a reference. But if you have questions or any doubts about this, well, you can ping any Max VPN engineer or any VPN engineer, and well, we can gladly help. Um, if you have any question, or please let me know or let us know.
Fernando, there's questions.
Okay.
For the anti-reply, for the Windows size, does it matter for example, there's a hub and spoke topology. Does it matter for the same? Should we use the same size on both sides, on the hub and spoke side, or should we have a different size? Does it matter?
Well, it is the best practice to have the same window size on both peers. So of course, if we have a VPN tunnel, we are going to send bidirectional traffic. So it will be better to have the same exact window size on both sides, on both peers.
So it doesn't matter on the topology. We should have a same window size.
Yeah, correct. And as you mentioned, in the hub spoke scenario, well, all of the spokes and hub routers should have the same window size.
Now I'm wondering because the hop side will receive more packet. Would that be higher chance to get a auto order?
Yeah, it will be a higher chance. So, of course, we need to verify and troubleshoot if indeed the packets are going to be dropped to that error. But yeah, there's of course, if the router is receiving a lot of traffic, and if the router is, for example, reassembling all of the traffic, if there are fragmented packets, of course, we're going to have uh, a more probable chance that these packets are going to be dropped to that.
Okay. Now another question. So this is only for iOS XE, right? Do you have any information on the Viptela VH?
Yeah, I put it here. It's the same. Well, basically the essence is the same, but I'm putting here a reference here about the security configuration guide for iOS XE, Viptela, and I put it here on this slide that the configuration in order to modify the IPsec anti-replay window, it's different here on this image. This is for iOS XE.
Right.
And this
No,
is for
not for Viptela.
Yeah, I mean, the Viptela are the VHS router that we have. Those are not iOS-XE SD-WAN, it's the SD-WAN devices itself. The configuration is pretty similar. However, for troubleshooting tools is a little bit more complicated since all the tools that we have, like packet tracer, capture, and this information is on the iOS-XE itself. So we don't have the same troubleshooting tool for the Viptela. I mean, we have the same concept for anti-replay on Viptela. However, troubleshooting is a little bit different from there, but it's not covered on this session.
Thanks, Amanda. The question, the reason I'm asking is I wonder if there's any things to watch for Viptela, like V edges when between V edges and C edges, because I think the window size is different. Right?
Yeah, so on Viptela devices, the window size starts from 512, right? Here on the iOS XE, it starts with 64. And coming to the IPsec tunnels, on the Viptela also we can configure standard IPsec, and we have the Viptela IPsec between the BFD, right? That IPsec. So that is not without the IC, right? We stripped out the IC and we did it, those tunnels, right? And if you want to particularly check the messages where you want to see the errors, you can check on where log messages folder, messages file, and you can enable some debugs as well. And messages will show what the error correctly is. So in my past troubleshooting, whenever we saw any issues, I used to look at where log messages. Okay. Yeah, and the negotiation comes like if there is a replay window configured on one endpoint and one Viptela device and remote device, right? Both have a BFD session, and whichever has, I believe, the lower replay window size is negotiated. So that's how we do it. And so when we see there is a replay drops, what we do is we either increase the replay window size or we do a rekey. Rekey also used to help in sometimes. So these are some of the pointers.
Okay, thank you.
Thank you, Regina. Thank you for that. Just to clarify on the iOS-XE, the anti-replay Windows ad is not negotiable. I mean, this is local significant for a device on iOS-XE.
Oh, on iOS actually. Okay, okay. On
Mhm.
Viptela, we
Okay.
do like hub and spokes are there, right? So what happens is like is like a small replay window, right? So we will negotiate that window. So you can configure on two endpoints and you can check it. So both sides should be done in order to be negotiated. We had some sequence numbers and some problems in the past. So where we did that part for some of our customers. Yes.
Okay. Perfect. Thank you for that.
Yeah, no problem.
Thank you, Rajendra.
I have a question about the, in terms of dropping the packet, I'm guessing we drop the packet before it gets decrypted, right? Because we don't even accept the packet as it's a legit packet, right?
Yeah, that is correct. Yeah, that is correct. So it's going to be dropped before it's going to be decrypted. So that is why we use the ESP sequence number.
I have a question. What I've noticed is it seems some complex QoS configurations can cause the anti-replay checks to fail. Is there guidelines on how QoS should be configured in order to avoid this? Because my understanding is the way we process QoS, you do the QoS processing after the IPsec encryption is done. And because of that, you could get some out of order or loss that cause these check failures to occur more frequently.
Yeah, there's a document that explains that. So if we open, I did not put this on the presentation because I don't want to focus on QoS, but yes, there's like some best practices and some notes that you want to take into consideration when configuring QoS, so we can avoid this kind of errors. If you want, Rodney, I can share that with you. I will add it here on the reference, so you can have
That'd be
it
great.
and take a closer look at it.
Yeah, because when people go like on SD-WAN, when people go into CLI mode, there's nothing really stopping you from configuring multiple priority queues, bunch of policers, and all this stuff can, once we hit high levels of throughput and we start hitting policers and multiple priority queues, that's when I've seen this, tunnels start going down. The router will just drop everything. It won't shape it to like 1 gig. It'll just drop everything. So that'll be really helpful to have.
Yep, I will share that with you. I will put it here on the references, and I will pin that document to you directly.
Awesome, thank you.
I have a question in terms of tracking sequences. So let's say that in the same example that you provided earlier, from 101 to 164, if I lost one packet of those because of QoS and I received the 63 other packets on the other side, do any of the two routers keep track of what sequences has been sent and received, or it will just be regarded as a packet drop and nothing more than that?
Now, in this scenario, the router won't keep track of those packets. So basically, the only thing that matters is the sliding window. So if, for example, as you mentioned, if you're using QoS, that packet is stored in the buffer because of a shaper or I don't know, a priority queue that was mentioned previously, and then it's sent towards the receiver. The only thing that will appear is like, okay, this is out of sequence because it doesn't match the sliding window, or we do not expect this kind of packet, so it is going to be dropped. So the router does not keep track of the packets that are missing or being dropped to that. So only it appears it's dropped, and that's all. That is why we need to perform this kind of troubleshooting to detect if the packet is being dropped to a configuration, a network design, QoS, etc., or it's being dropped because of an attack. That is like a limitation. Let's say it, a limitation on the router.
Understood.
Okay. Any other question?
Good stuff, Fernando. Thank you so
Okay.
much for this.
No problem. Thank you very much for joining, and hope this presentation is helpful. We will share this